we came up with the definition of a logarithm. So to remind you, we said that if you take log base b of x and you get y, what exponential equation would be equivalent to that one? Has the exact same information, but written as an exponential equation. B to the y equals x. Yep. So b is your base. It's your base in both forms, right? It's the base of the logarithm. It's the base of the exponent. And then logs are exponents, right? So this log is equal sign is the exponent. So y is the exponent, and that should equal x. So this is what logarithms are. They undo exponentiation. So let's do a quick example. I want you to find log base 5 of 625. So when I write that, I'm asking, remember this is the liftoff thing, I'm asking you to rewrite 625 as 5 to the something. So I'm going to rewrite 625 as 5 to something, to the fourth. Good. So just rewrote the 625, rewrite 625 as 5 to the fourth, because they told me what base to use to rewrite it. And then the logarithm is the liftoff function. And then you lift off the exponent and you get 4. Coming back to you? Okay. All right, so now we're going to talk about some basic properties of logarithms. So for A here, we're going to look at log any base, just any generic base of 1. 0, can you explain why? B to the 0 is 1. Yes, so what I'm trying to do is rewrite 1 as b to the something, and no matter what b is, if you raise it to the 0, you get 1, because anything to the 0 is 1. And then when I do liftoff, I get 0. So log base b of 1 is 0. Doesn't matter what the base is. Log base 5 of 1 is 0. Log base 23 of 1 is 0. No matter what the base, if you take the log of 1, you get 0. All right, no, part B here. Log base b of b to the x. X, right? The bases already match, right? I have b and b, just lift off the exponent. Once the bases match, you just lift off. So for C here, we have b to the log base b of x. What do you think it is? I've heard a couple people whisper it with not very much confidence. X, yeah, it's x. So let's see if we can talk about y. B to the log base b of x. So b to the log base b of x. So it looks kind of complicated, right? You're like, it's a little overwhelming. So let's just say we're gonna simplify this by saying let y be log base b of x. Right? So then I can just replace this. This just says b to the y, right? Okay. So, but if I change this sentence that I just wrote to an exponential equation, what does it say? B to the y equals x, right? b is my base, y is my exponent, equals x. So that means that this has to equal x. So log b to the log base b of x equals x. It feels circular because it is, right? It's a round trip. B to the x and log base b of x are inverse functions. It should give you a round trip. When you compose one into the other, we should get x back. So that it feels circular because it is. Yeah. So that's why we get, it's kind of like saying, what is the name of the boy named George? Right? So, and you're like, George. So that's why it comes out to x, right? It just feels like, okay. Okay, so here's my next one. My next property, log base b of x times y. If I want to simplify that, it turns out to be log base b of x plus log base b of y. So it looks kind of like I'm distributing that log, but it turns into a plus sign. And the reason for that is because logs are exponents, right? And when you multiply when you have like bases, you always add the exponents. So if I change these, let's let a be log base b of x. So this is just a little explanation or a proof of why this law is what it is. Let a be log base b of x. Oh, I don't like those letters because I already have a b. M, let's use m. M will be log base b of x, and n will be log base b of y. So change both of these to an exponential equation. This first one, what would it say? Right? B is my base, m is the exponent, equals x. And then n equals log base b of y. How would that be changed to an exponential equation? B to the n equals y. Good. So this is just some preliminary work. Now I'm going to start here and prove that it equals the right side. So log base b of x times y. All right, so, well, x is b to the m. So this says log base b of b to the m times y, which is b to the n. What is b to the m times b to the n equal to? M plus b to the m plus n. When you have like bases, the rule of exponents is that you add the exponents together. So this is log base b of b to the m plus n. So what is log base b of b to the m plus n? M plus n, right? The bases match. Bases match, just lift off the exponent. But what is m? We go back a little bit here. Log base b of x, and n is log base b of y. So we proved it. This equals this. Okay? And the reason it happens is because we had to use laws of exponents along the way. So logarithms follow the rules of exponents because logs are exponents. Any questions there? So in general, as long as you could sort of follow what I just did in this proof, I'm not going to ever ask you to do this on your own. You need to be able to use this property, remember this property, and apply it. but I just wanted to show you why it is what it is. But I won't ask you to prove it on your own. All right, so here we have log base b of x over y, and it equals log base b of x minus log base b of y. So we have the log of a division problem turns into a subtraction of two logs. So it's analogous to this one. The log of a multiplication problem turns into an addition, division turns into subtraction. And we have a really similar proof. Okay, so we would do the same thing. We would let two letters m be log base b of x and n be log base b of y. Change these to their exponential form. Oops, that's an x. So there's just some preliminary work. Now I'm going to go ahead and do my actual proof. Start here, log base b of x over y. And now I'm going to replace x and y with b to the m and b to the n. Okay, so I have log base b of b to the m over b to the n. How do I simplify what's in parentheses there? Yep, b to the m minus n. The law of exponents says that when you're dividing like bases, subtract the exponents. And then I can, now my bases match, I can just lift off and I get m minus n. Right? But m, if you remember, scroll up a little bit, is log base b of x. And n is log base b of y. So it makes perfect sense that division would turn to subtraction because that's the law of exponents. When you're dividing like bases, subtract the exponents, and logs are exponents. So it follows that rule. All right, one. Yeah, sure. Okay, the most useful law of logarithms. Log base b of x to the p is equal to p times log base b of x. It looks like you just take the exponent and drop it down in front. Okay. So the reason for this has to do with the law of, that was addition that we did before. So if I do log base b of x to the p, x to the p just means repeated multiplication, x times x times x times x, p times, right? So this says log base b of x times x times x. And I have p of these. So then I do my property from 2 back, right? The one that talked about multiplication, where you're taking log base b of the product of two things. It changes to a sum. So I have a product of multiple things, so it's going to become a multiple sums. So this is going to be log base b of x plus log base b of x plus log base b of x plus log base b of x. So it looks like I'm distributing this log to all my x's and they're connected with addition signs. And how many of these log base b of x's did I write here? P. There are p of these. And repeated addition, I could write as multiplication. I have p log base b of x's. So I have now shown why this equals this. All right. So I've shown you where they all come from. We're going to use some of them. Okay, so this is the important thing. This is what you really need to be able to do. You need to be able to recognize what law applies and apply it. So I have log base 4 of 2 plus log base 4 of 32. They have the same base, and it's addition, right? So I can use this law. Same base, and I'm adding them, so I can go backwards this way. So that says I can write them as a single logarithm where I multiply the two inputs. So I could write this as a single logarithm of 2 times 32. So that would be log base 4 of 64, which is what? 3. Yeah, because this says rewrite 64 as 4 to the something, and that would be cubed, and lift off the 3. Okay, so now I have a subtraction. I could combine them by doing what to the two inputs? Dividing. So I would write this as a single logarithm where I divide the inputs. So this is log base 2 of 80 divided by 5 would be 16, yeah. And what's log base 2 of 16? 4. Because I could rewrite 16 as 2 to the 4th, which would be 4. All right, and now here's an example where I use the x to the p one. Okay. Log base 2 of 4 cubed. I can take my exponent. And drop it down in front. So this is going to be 3 times log base 2 of 4, which is 2. So I get 6. Could I have done this one a different way? Ah, I see. Yes, do 2 squared, multiply the powers 4 times 3, so I would get 2 to the 6th, right? So I would say, well, log base 2 of 4 cubed. That's log base 2 of whatever 4 cubed. Oh, I can rewrite 4 as 2 squared and cube that. And then that's log base 2 of 2 to the 6th, because when you raise a power to a power, you multiply, and then we can just lift off the 6. So you can do it either way. You can use the property of logarithms where you can bring the exponent down in front, or you can just evaluate that number in parentheses and write it as 2 to the something. Mm-hmm.
When you're getting the 2,
yeah.
You're getting that. Are you getting that from the 4?
Yep, I'm rewriting the 4 as a 2 squared. And the reason I chose to write it as 2 squared is because my base was 2. And so the thought process is I would like to rewrite 4 cubed as 2 to the something because the base is 2. So I said, well, 4 is 2 squared. I'll start there. Okay, now I'm going to have you try for the last 5 minutes. Work on this activity. And do at least a couple from 1 and a couple from 2. And if you have questions, let me know.